Hello students. Today we are going to discuss about variations in transportation problem. In time of solving transportation problem, we face some difficulties. First, we have to resolve the difficulties, then we can solve the problem by usual methods. Now, the difficulties may arise in different ways, like unbalanced supply and demand. Degeneracy. We have already discussed little bit about degeneracy. Here we discuss the problem in details. The degeneracy may arise at the initial solution and also it may arise during the subsequent iteration. Another kind of problem is called prohibited transportation routes. That means there are some particular routes which cannot be availed. That is, we cannot make allocations in some particular sales. This kind of problem can be resolved by assigning a very high cost to that corresponding sales which routes are prohibited. And we may face another kind of problem if the transportation problem is a maximization problem. Now we will discuss these difficulties one by one. First of all, we discuss about unbalanced supply and demand. If for a given problem, total supply is not equal to total demand, we say that it is an unbalanced transportation problem. We have to first resolve this problem. Then we can solve the transportation problem by the method we have already discussed. Now, if for a given problem, if total supply exceeds total demand, in that case, we have to add a dummy demand center. We have to create a dummy demand center with the excess supply as the demand of that center. Now, the unit transportation costs for the sales in this column, that means in these dummy demand centers, are assigned as 0. Similarly, if total demand exceeds the total supply, we have to add a dummy supply center with the excess demand. And also the transportation costs for this row are also assigned as 0. Now the problem becomes a balanced transportation problem and we can solve the problem by the normal transportation methods. Let us discuss the problem in details by considering an example. In this given transportation problem, we see there are 2 sources and 3 destinations. And the availability at the sources are 80 units and 50 units. And the requirements of the destinations are 30 units and 40 units. So the total supply in this case is 80 plus 50, that is 130, and total demand in this case is 30 plus 30 plus 40, that is 100. Here we see that this is an unbalanced problem. So we have to make this problem, convert this problem to a balanced one first. Here we see that supply exceeds demand. So we have to create a dummy demand center. That means we have to introduce a dummy column, the fictitious column with this excess with this excess supply, that is here our total demand is 100 unit and total supply is 130 units. So 30 unit is excess. So we introduce this fictitious demand center, dummy demand center with demand 30 units. And we put unit transportation costs to the cells of this column as 0, so that the allocations in this column will not affect the total transportation cost of the problem. Now this transportation problem is a balanced one, and we can solve this problem by the usual method which we have already discussed in our previous lectures. Next we discuss about degeneracy in transportation problem. A basic feasible solution is called degenerate if the number of positive allocations is less than m plus n minus 1, where m is the number of rows and number of sources and n is the number of destinations. So if positive allocations is less than m plus n minus 1, then the solution is called degenerate basic feasible solution. In this case, we cannot improve the solution we cannot improve the solution. We cannot test the we cannot do the optimality test of the solution, and also cannot improve the solution because we cannot evaluate the quantities ui and vj's for the optimality tests. So we need to resolve the degeneracy to improve the solution. Degeneracy in the transportation problem can be resolved by making unoccupied cells as occupied. And we know that for a non-degenerate basic feasible solution, number of occupied cells must be m plus n minus 1, where m is the number of sources and n is the number of destinations. So number of occupied cells must be m plus n minus 1. So we have to make unoccupied cells as occupied. As many allocations are required to have m plus n minus 1 independent set of allocations, and this allocation is done by a very small quantity epsilon close to 0 to the unoccupied cells. In case of minimizing transportation problem, this quantity is added to the cells which have lowest transportation costs. And also in time of allocating, we have to make sure that the quantity added in such cells that does not result in forming a loop among or all of the occupied cells and make them dependent. That means we required an m plus n minus 1 independent set of allocations. Let us consider an example. In this transportation problem, number of sources is 3 and number of destinations is also 3. And also the total supply is equal to total demand for this problem. So this is a balanced transportation problem. Now an initial basic feasible solution of this transportation problem is x13 equal to 60, x21 equal to 50, x23 equal to 20, x32 equal to 80. Here we see that the number of allocations is equal to 4 and the value of the quantity m plus n minus 1 is equal to 5. So the solution, that is this initial basic feasible solution, is a degenerate basic feasible solution. And the optimality test of this solution is not possible, and we cannot also improve the solution, as the number of allocation is less than m plus n minus 1. We cannot calculate the values of the quantity ui's and vj's from the relation ui plus vj equal to cij for the occupied cells. So we have to first resolve the degeneracy of the solution for test the optimality and improving the solution to an optimal basic feasible solution. Now, as the number of allocation is less than m plus n minus 1 by 1, so we have to make one of the unoccupied cell as occupied for a non-degenerate basic feasible solution. For this, first we have to select an unoccupied cell with minimum transportation cost. And also we have to keep in mind so that this selection cannot form a loop with the occupied cells, so that can make the solution dependent. But we have to find a set of solution which are independent. That means allocations must be independent. Here we see that the cell 3, 3 is of minimum cost, and also if we allocate in this cell, this will not form a loop with the other occupied cells. So we allocate epsilon to the cell 3, 3. Now the number of occupied cells is, that is number of positive allocations is 5, and which is equal to m plus n minus 1. So this solution is a non-degenerate basic feasible solution, and we can test the optimality for this solution, and also we can improve the solution using the usual method we have already discussed. Now let us calculate the quantities ui and vj's for optimality test. We calculate the quantities ui and vj with from the relation ui plus vj is equal to cij for the occupied cells by putting arbitrarily v3 equal to 0, as in the third column maximum allocation was done. So v3, we put v3 equal to 0, and from this we can at once write u1 equal to 3, u2 equal to 9 and u3 equal to 5. And with the help of this we can write v1 equal to minus 6 and v2 equal to minus 2 from the relations ui plus vj equal to cij for the occupied cells. Now we calculate the quantities ui plus vj for the unoccupied cells. This is one unoccupied cell, and ui plus vj equal to minus 3 for this cell, and ui plus vj for this cell is 1, and also it is for this cell is 7, and for this cell it is minus 1, that is minus 6 plus 5 minus 1. Now we calculate the cell evolutions for the unoccupied cells, and we put dot in the occupied cells. The cell evolutions are calculated from the relation delta ij equal to cij minus ui plus vj, and here we see that the cell evolutions are 11, 6, 1, and 12. All the cell evolutions are positive. So the solution we considered is an optimal solution. And the solution is x13 equal to 60, x21 equal to 50, x23 equal to 20, x32 equal to 80. And also x33 equal to epsilon, but as epsilon is very small quantity, we neglect that, and the minimum transportation cost is 750. Now let us discuss another kind of transportation problem, which is maximizing transportation problem. There are certain types of transportation problem in which the objective is to maximize the total value, that is, we may consider it as profit. So in this problem, instead of unit transportation cost Cij, the unit payoff or the profit associated with each route is given. So this in solving this type of problem, we have to first convert this maximization problem into a minimization one. And this is done by subtracting all the entries of the cells from the highest entry in the given transportation table. Then the modified problem can be treated as the minimization transportation problem, and we can solve this problem using the usual method we have already discussed. And when we find the total profit, we just use the given transportation table, that means maximization table, in time of calculating the value of the problem. Let us consider an example. This is a maximizing profit problem. In these cells, the unit profit or unit payoff is given, and also this is a balanced problem. Here we see that highest profit is in the cell 3-1. It is 90. So first we convert this maximization problem into a minimization problem by subtracting all the entries from 90. Highest element is 90, so we subtract all the entries from 90, and we get the modified transportation table as 90 minus 15, that is equal to 75, 90 minus 51, that is equal to 39, 90 minus 42, that is 48, 90 minus 33, that is 57, 90 minus 80, that is 10, 90 minus 42, again 48, 90 minus 26, it is 64, and 90 minus 81, it is 9, 90 minus 90, it is 0, 90 minus 40, it is 50, 90 minus 66, it is 24, and 90 minus 60, it is 30. Now this can be treated as minimization transportation problem, and we can solve it using any one of the method discussed earlier. So the modified minimization transportation problem is given by this table. Here we see that there are 3 sources and 4 destinations, and also this is a balanced problem. So using VAM method, the solution, initial basic feasible solution of this problem is obtained as x12 equal to 23, x21 equal to 6, x22 equal to 8, x24 equal to 30, x31 equal to 17 and x33 equal to 16. Here we see that the number of allocation is 1, 2, 3, 4, 5, 6. Number of allocation is 6, and which is equal to 3 plus 4 minus 1, that is equal to 6. So this is a non-degenerate basic feasible solution. Now we test the optimality of this solution by calculating Ui and Vj's for the occupied cells first. Here we put U2 equal to 0 because maximum number of allocation is in the second row. So we put U2 equal to 0 and we calculate at once V1 equal to 10, V2 equal to 48 and V4 equal to 9. With the help of this, we can calculate the values of U3 equal to minus 10, V3 equal to 34 and U1 equal to minus 9. Using this Ui and Vj, we calculate the Ui plus Vj for the unoccupied cells. And Ui plus Vj for the unoccupied cells are 1, 25, 0, this is 34 and this is 38 and minus 1. Now we calculate the cell evolutions. The dotted cell are the occupied cells and we calculate the cell of evolutions for the unoccupied cells from the relation delta ij equal to Cij minus Ui plus Vj. And the cell evolutions are all, we see that the cell evolutions are all positive. So the solution under consideration is an optimal solution, and as all the cell evolutions are positive, so this is the unique optimal solution of the given maximizing transportation problem. And the solution is this is the solution which we have already obtained by using VAM method. Now in time of finding the profit, maximum profit, we use the given transportation table, and the maximum profit is given by this 23 into 51 plus 6 into 80 plus 8 into 42 plus 81 into 30 plus 90 into 17 plus 66 into 16, and that is equal to rupees 7,005. And that's all for today. Also, this is my last lecture on transportation problem. Thank you all for listening me. If you have any problem in understanding transportation problem, or if you have any suggestion, then don't hesitate to mail me on email to nmunshi@gmail.com. Thank you once again. Goodbye.